Okay, I think we can start. It's my pleasure to introduce Professor Gaurav Arya, a professor of mechanical engineering and material science, biomedical engineering, and chemistry at Duke. His research lab uses physics-based computational tools to provide fundamental and molecular level understanding of diverse range of the biological and soft material systems, such as composite material and nanoparticle and polymer composite and DNA translocation models. And those researches are funded by substantially from NSF, DOE, and NIH. Yeah, so please join me. Welcome Professor Gaurav Arya.
Thank you. Can you hear me at the back? Probably don't even need this, but I'm audible, right, at the back? Okay, great. Well, thanks, John, for the lovely introduction and for inviting me. This is, I think, the fourth time I'm visiting the campus. And I always have a wonderful time. And as usual, today also I'm having a great time. It's not too far. I'm just from up north I-40 or I guess west. So please do visit our campus. It's equally beautiful like yours. All right. So today I thought I'll talk about a couple of stories from our kind of ongoing research activities. And both stories actually involve self-assembly. One of them involves self-assembly of nanoparticles into interesting architectures. And the other one involves self-assembly of DNA or DNA-Origami structures into, again, interesting architectures, but more importantly, interesting functions. Okay, so those are the two things I'll talk about today. And before that, I thought I'll tell you a little bit about what we do in our research group, maybe a minute or two. So we are essentially a molecular modeling and simulation lab. So by molecular simulations, I mean things like ND simulations, Monte Carlo, Brownian dynamics, you name it. Okay, anything that has a simulation in it, we do it. Okay, so what these simulations allow you to do is calculate or compute properties of materials from molecular structure and interactions, as many of you may already know. Just a small overview of how these things work. So let's say you want to model water. Okay, so the way these things work is you take a small volume element of the material that you're interested in, and you model it as made up of a bunch of particles. Now, these particles could represent individual atoms, molecules, sometimes entire polymers, sometimes entire nanoparticles. Depends what resolution you're interested in. And they usually interact with classical force fields or potentials, interatomic potentials, that are usually derived from quantum mechanics, at least at the scale of atomistic. Of course, if you want to study polymers and you want to model each as a polymer, you get basically that effective interaction potential from simulations of atomistic models of polymers, okay? And not directly from quantum mechanics. Okay, so the configuration of these systems, you put it in a simulation box, and they're usually described in terms of the position vectors of each and every particle in the system and the momentum vectors, okay? So once you specify that, you've completely described the system, okay? So what the simulations do is essentially sample representative configurations of these systems such that they are consistent with certain laws of physics, okay? Newton's laws of motion is one aspect that they have to conserve, okay? The other is, if you are simulating this at constant temperature and volume, you have to satisfy certain distribution functions that are derived from statistical mechanics, like the Boltzmann distribution that you would have heard of. So essentially what we're doing is we're just pretty much making movies of everything, okay? So it's fun. It's a lot of fun, okay? And then you can analyze all these configurations. There are many, and you typically use supercomputers for getting them, okay? And then you usually use the theory of statistical mechanics, certain equations from statistical mechanics, certain correlation functions from statistical mechanics to derive these material properties. So that's kind of the gist of what we do, and that's the only technical slide I have here. But hopefully you get a flavor of the application of these kind of tools towards various problems that we are studying. Okay, so in our lab we use these molecular simulation tools and other tools from analysis, theory tools. Polymer physics is something we use a lot, colloidal physics. Machine learning is something we are starting to use a lot. And we applied it towards addressing two problems, biophysics and nanotechnology, and often at the interface of the two. Okay, so one of our long-standing interests is in genome organization and regulation, where we've been building a hierarchy of models to understand chromatin organization or DNA organization inside us, basically, living systems. All the way from nucleosomes to chromatin fiber to chromosomes. That's a long-standing interest, though it's kind of waning at the moment. Okay, and in fact, I won't talk about it today. Another, I would say, a more recent interest is in viral DNA packaging, where we are interested in how this tiny little motor, which is one of the most powerful motors known to mankind, packages DNA inside certain viruses called bacteriophages. These are viruses that attack bacteria. And it happens through really exquisite mechanisms with a lot of coordination between individual subunits within this motor. And we are interested in the mechanisms of how that happens. Okay? That's another story I probably will not talk about today. Okay? Too much biophysics there. Okay, instead, what I'll talk about is these two kind of themes in our research. The first one is in nanoparticle polymer composites, which I think is kind of relevant to this mechanical engineering department, where we are trying to come up with ways to organize or self-assemble nanoparticles. Usually these are made out of silver and gold because we're interested in plasmonic applications, light matter interactions, into interesting architecture that may be useful for those applications. Okay, that's one thing I'll talk about. I'll start off, in fact, with that. And then I'll talk about another story within DNA nanotechnology, where we are trying to introduce dynamic mechanisms into generally otherwise static origami structures. And we are also trying to assemble these dynamic devices into larger arrays so you can take advantage of some collective behavior or emergent behavior that kind of emerges from that. All right, so starting with story number one. Okay, so just an introduction. All of you will probably know that incorporating nanoparticles in polymers is good, right? It enhances thermomechanical properties of the polymer, whether it's viscoelastic properties, fracture toughness, and so on and so forth. Okay, and this enhancement occurs due to two main reasons. One is an obvious one. Nanoparticles have different properties. They are hard, right? Polymers are soft. So basically, the polymer composite will have a property intermediate to the two, right? That's kind of obvious, okay? But a more subtle, but actually a more stronger effect is because these nanoparticles introduce interfacial and confinement effects. So they change the properties of the polymer at a very fundamental level. And this happens even at extremely low volume fractions, like 1 or 2%. And that's enough to completely change things. Okay? So other than enhancing properties, you can also introduce new properties, optical, magnetic, catalytic, I named some of them, magnetic, so on and so forth, into the polymer. So that's more, I would say, a polymer-centric view. But the nanoparticle-centric view is you use the polymer just as a guiding principle to embed these nanoparticles within. So you could put a third point in there, okay? All right, so that's probably enough of composites. Okay, so now most traditional composites so far that you have encountered in aircrafts, in your car, in insulation, reinforcement, they're kind of boring. So you put nanoparticles, you want your nanoparticles to be dispersed, okay? Because you don't want things aggregating in a certain way and depleting from another, and you get non-uniform properties, okay? So, but some of the newer, more sophisticated applications, and I'll talk about one of them, would want these particles to be assembled either into clusters or higher order arrays, okay? Architectures where you can take advantage of these collective properties of these nanoparticles, okay? And this is especially important in the so-called plasmonic nanoparticle composites, okay? Where you would want to arrange plasmonic nanoparticles made out of gold or silver. These are the plasmonic materials because they interact with light in a certain way. They have their intrinsic frequency of their electrons matches that of incident light, and you get very interesting properties. You get electric field enhancement that you can use for Raman spectroscopy and so on and so forth. Okay, a lot of applications that are coming up. Okay, so you want to arrange these into clusters or arrays so that you can take advantage of these very unique resonances that arise from these coupling effects. And the applications that come up from them. And I told you Raman spectroscopy is one of them. So with particles arranged very close to each other but not touching each other, you get extremely high electric fields in the region in between, which are called hotspots. And you can enhance Raman signals that you use for characterizing materials almost 1,000,000-fold, and even more, in fact. Okay, so that's one obvious application, and there are others also. Okay, I'm not going to go into the details of that because my talk is not about applications, actually. Okay, now, unfortunately, achieving unique and complex particle arrangements, which you would want to create interesting resonances, interesting coupling effects, is challenging so that you can explore these new applications. Okay, what I mean by that is if you take your off-the-shelf nanoparticle, typically, which are usually spherical in nature, they usually interact with very simple kind of DLVO type potentials. They may have a single energy well and maybe a small barrier, but not a very long range barrier. Okay, as long as you don't have that, and as long as you don't have multiple energy minima in that potential, they would basically self-assemble into boring hexagonal, basically close-packed structures, right? Because they want to maximize the contact between them, FCC or HCP. That's in 3D. In 2D, they would basically form triangular lattices, okay? Again, to maximize contacts. Okay, and this is assuming that the particles are perfect, right, spherical, and these assemblies are happening at equilibrium, which can also be challenged, okay, because these things tend to aggregate, okay? Okay, so what we do in our lab is basically come up with strategies, usually from simulations, inspired by simulations, in collaboration, close collaboration with experimentalists, so that we can assemble these particles into interesting architecture, whether it's using different shapes of particles, whether it's functionalizing them, whether it's taking advantage of multi-body effects that arise from the functionalization of these, or whether you use interfaces to break symmetry. All these ideas we are pursuing, okay? So that's kind of a major part of our research effort, is collaborating with experimentalists and helping them in some ways. But of course, we are a theory group, so we are also interested in understanding fundamentals. So we build energy landscapes, we build phase diagrams, and so on and so forth. We try to understand dynamics. We do image analysis of composites and stuff like that. Sometimes we will find that some of the methods that we're using are very inefficient, so we'll develop models or methods to improve them, and so on and so forth. And of course, ultimately, we want to understand the property of the material that emerges out of this. So we are also interested in property prediction, okay? Okay, so today I thought for this purpose of this talk, I'll focus on some of our more recent efforts on interfacial assembly, where we have come up, or I wouldn't say develop, I would say propose, because it's purely computational. Okay, we are working with experimental collaborators to test some of our predictions. So I'll talk about an interfacial assembly approach that basically allows you to assemble even spherical particles into very interesting architectures, including quasi-crystals, which I actually won't touch upon today. Okay, so that's what I'll talk about today. And there's some aspects of method development that I'll show here. Okay, all right. So the other thing I also wanted to say is we are fine with using any scales as long as the problem works. So many of these phenomena occur across different scales. So we are open to using atomistic, coarse grain, or even very coarse, what we call mesoscopic models, and sometimes analytical theory wherever is possible. So it's a multi-scale approach, okay? All right, so let me tell you this method directly, jump into it, okay? So our method hinges on three key ideas, okay? Number one is we take advantage of the surface tension between two mutually immiscible fluids. They don't like each other, okay? To trap nanoparticles there. So if you have a nanoparticle that's neutral, not charge-wise, okay, but neutral in the sense that it likes both fluids equally, or it hates both fluids equally, okay, but not too much, okay. In that case, what you'll find is that the nanoparticle will sit directly at the interface so that it can occlude the maximum area of the interface, because remember, the interface is unfavorable here, right? Now, if you have lots of these particles and they all go to the interface and they start to self-assemble, if they had some attractive interaction between them, unfortunately, this is what you're going to get. You're going to get the same triangular lattice or hexagonal lattice, packed lattice. Not interesting. Been done, okay? So that brings me to my second idea. What if you could functionalize these guys with molecules or polymers, in our case, such that that polymer likes one of the fluid versus the other, okay? This way, you can displace the particles away from the interface, because it wants to also interact with that fluid that it likes, but it still wants a little bit of that piece of that interface, okay? Because it's favorable, okay? So you can think of it as, let's say you put this green polymer, which likes this green fluid over here, and it's going to get displaced. The amount of material you put on it, it'll get displaced more and more because you have stronger and stronger interaction. That's why you see this blue guy only getting displaced a little bit, because it has a smaller grafting density, okay? Unfortunately, if you individually self-assemble these, they're going to give rise to the same boring structure, okay? So now comes the third idea, which is a key idea. What if you mix the two species together, okay, and co-assemble them? Now, these two particles, here you have 6 neighbors here. When you have 2 particles, you would want to form a bilayer because you can gain 3 more interactions, assuming it's a hexagonal packed layer. You'll get 3 more interactions from there, but that could cost you some energy, because your voids may be either too far, so they need to squeeze together the 2 layers, or you have too much sterics and you have to push apart the voids, right? You're clashing with each other. So that will cost interfacial energy, because you're going away from their preferred trapped position. And what I'm going to show you today is this kind of interplay or tug of war between interparticle forces and interfacial forces actually gives rise to very interesting assemblies due to this frustration, okay? All right, so to tackle this problem, we turn to our basically bread and butter, which is MD simulations, okay? So we built, and I'm not going to go into the detail, but we basically built a very simple generic coarse-grained model of the system that captures the essential physics of the system. I'm not going to go into the details of this, but it can capture things like interfacial tension, capillary fluctuations, conformational properties of these chains, and so on and so forth. The fact that one chain likes one fluid versus the other, and so on and so forth. Okay, the fact that you have extruded volume interaction, all that stuff, nice stuff, basically. Okay. And the first question we asked is, okay, we started by asking like, okay, how will a single particle behave? Okay, can we even tune the vertical positioning of these particles? Okay, so the thing we did was we calculated the free energy profile of a single particle grafted with a polymer that likes one of basically the fluids over here. I call it polymer here. It was a polymer actually, but it doesn't need to be. It could be oil, water, could be just fluids. Okay, doesn't matter. Okay. And here I'm plotting those free energy profiles, okay, as a function of bringing this particle to a distance z, okay, all the way from the bulk, so it has zero free energy over here, okay, for 5 different cases. One is a neutral particle, which basically, sits flat at the interface perfectly, and then the others are with increasing grafting density of this polymer that actually hates this guy here, but likes this fluid. Okay, so you can see all of them basically exhibit this quadratic sort of profile. Okay, just to give you an idea what this interface and what the particle size looks like relative to the interface, this is what the size is. Okay, so each of these has a minima. Okay, and that minima tells you basically the stability point, the minimum free energy state of that system. That's where it wants to be and fluctuate around. Okay, and you can clearly see neutral particles sit right at the interface because they like both fluids equally. But as you graft more and more of this polymer that doesn't like the other fluid, they start to deviate. It tries to go back into the fluid that it likes. Okay, because you see it's green polymer over here. Okay, it turns out that this very simple these free energy can be described by a very simple mathematical model for calculating free energy that calculates basically the free energy of bringing this particle from the bulk fluid over here to the interface at distance z from it. And it consists of 2 terms. One is a free energy gain, right? Because you're intersecting part of the interface, which is good because those interfaces hate each other. And that simply equals to the cross-sectional area multiplied by the surface tension of the 2 fluids, right? Very simple, okay? That's gained, so it's a negative, okay? On the other hand, free energy is lost in a way that is unfavorable, okay? Because you're taking part of this shell, this surface over here, and this cap. All this is good, but this cap is very bad because it's interacting. You're forcing it to interact with the unfavorable fluid, okay? So what's the energy corresponding to that? Is the area of this cap multiplied by the difference in the surface energy of this polymer interacting with this fluid and that fluid. Very simple, okay? It turns out that this very simple model can basically fit all the data over there, okay? And it can also, not only that, but you can also start to quantitatively predict a lot of different properties of this system, okay? Things like where is the trap location, and how it rises, how you deviate more and more with increasing difference in this surface energy of the polymer with the 2 fluids, right? And so on and so forth, trap curvature and the free energy. So you can predict. I'm not going to go into details, okay? So now that we have shown that you can trap particles at almost reproducible, whatever you want distances from the interface by changing basically just this one knob, which is the grafting density. Let's see now if you have multiple particles at different planes, trapped at different planes, and making them interact with each other and introducing this frustration, what kind of assemblies will they form? So we started with the very simplest possible system, which is just 2 particles, what we call antisymmetric particles, where they are identical in all respect, except this guy is grafted with this polymer and this guy is grafted with this, so they'll basically equally get displaced in opposite direction. Okay, and again, the results are kind of very obvious, right? If you have a neutral particle, they'll stay at the interface and they'll just form dimers like this. But as you graft more and more of these particles get pushed further from the interface and therefore interact at these larger tilt angles. Okay, so very straightforward, nothing, but just to test. Okay, then we said, okay, let's try something a little bit more challenging. Okay, let's try to make a trimer, which is very challenging, which is open. Okay, because normally you would just basically collapse, right? This is a homework problem in my simulation class. What's the minimum energy configuration of 3 particles or 3 atoms, right? It's a triangle, equilateral triangle, right? Because you get these 3 nice interactions. Okay, so our idea was if you could trap one particle at the center, okay, by either choosing a neutral particle or grafting it with neutral polymers that are neutral to the 2 fluids, trapping another particle well below the interface with a lot of grafting so that you can push this to an almost 90-degree angle, and then grafting, and then using the grafting density on the other particle, which the polymer that likes the other fluid, and tuning that grafting density to change the angle. And in this way, you can actually form these water molecule-like clusters where you can change the bending angle between them over here with small grafting density, large grafting densities and even larger grafting densities. So you get almost vertical configurations. Of course, without anything, without any polymer, you'll form these trimers. Okay, so all this was good. Okay, so this is the system I just showed you, right? But then you will ask the question, well, I mean, you're cheating, right? You just put 2 particles in there. Yeah, I mean, but in reality, you'll have lots of particles, right? And they'll all want to assemble. Okay, so that's what we were interested in. Actually, that's what we are actually interested in. It turns out, actually, these dimers, by the way, are actually stable. So these guys are not actually going to assemble because they have a nice steric coat of polymers around them, that if you try to bring other guys in there, it's going to introduce entropic repulsion because you're squeezing these polymers together into a tiny confined gap, which it doesn't like. Okay, but these guys at low density or intermediate density will start to assemble, actually. Okay, they're never going to form stable dimers like this. Okay, so that's what we did. So we took basically just 6 of these, of each of these, rather than 2 of these at these low densities. And at very low density, grafting densities, we find that they form a ridged hexagonal monolayer, which has not actually been observed, though it has been kind of predicted in very other completely different systems, like colloidal particles between 2 flat plates, which has some very interesting analogies to something called the Ising lattice. But in any case, I won't go there. But it basically forms alternating lines of upward and downward facing, which is kind of, again, a little bit obvious, but it's still a novel structure. Okay, an even more interesting structure is you form, rather than forming a hexagonal bilayer, you actually form a square, interdigitated square bilayer, which is kind of unusual. Okay, because if you think about it, hexagonal bilayer has 9 contacts per particle, right? 6 with its own layer and 3 with the above, right? This guy would actually have 8 contacts. So why does it do that? Very simple reason. Okay, this guy has bigger voids, so they can easily fit within each other without sacrificing too much. So they just need to displace 0.7 sigma or 0.8 sigma. This guy, these particles need to displace a lot from their favored position. So that ends up actually costing a lot of energy. So they form basically a square lattice. Okay, so far I've shown you basically, actually, you know what? I have one more slide here. Okay, so it turns out that you can apply these concepts also to create quasi-1D structures. But you have to borrow another concept of multi-body interaction. And I'm not going to go into detail, but the gist of it is, if you have a dimer of particles that have somehow assembled, so ultimately these guys, even though you have steric repulsion due to the polymer, that's entropic repulsion, the interparticle interaction from the cores is attractive, and they form a dimer, right? So normally you would think, well, if you put another third guy, it's going to go there. It turns out that this, due to multi-body effects, this steric repulsion becomes magnified, okay? And it doesn't actually want to form 2 contacts. In fact, it prefers forming 1 contact, but at least it has less steric repulsion. So that actually ends up being more favorable. So you'll form 1D structures in solutions. This is a totally emergent effect, okay? This has been done in bulk. So we borrowed this idea, and we found out that actually you can use this idea even in our system. So if you choose intermediate grafting density where you get these multi-body effects, you can actually form very interesting architecture, which I would say are actually even more interesting because they're purely emergent. You can't predict them. Like the serpentine structure over here, where you'll form basically these alternating lines. Each of these dimers actually, this is actually the same dimer that I showed you earlier, but it doesn't want to form 2 contacts. It wants to form only 1 contact, okay? So that's why this guy will form 1 contact, 1 contact, 1 contact. Here is a trimer structure, okay? That's going to form 2 contacts with another trimer, with a particle of another trimer, if it was below the interface, okay? So that's where you'll see this. So these 2 guys are below the interface, this guy's above the interface. These 2 guys are actually on the same fluid. So in the same fluid, you only form 1 contact. In the opposite fluid, you form 2 contacts. So you can form these tri-branch particles, okay? So now comes that slide that I wanted to talk about. So far, we have shown, okay, great, you can do all this very cool stuff, but we have used very simple systems, right? Like antisymmetric particles, especially for these 2D superstructures, or superlattices, what we call. Things like particles have to be the same size, same amount of grafting density on this, right? What if you wanted to explore the entire breadth of structures, right? That is possible with this approach, right? Different particle sizes, different grafting densities, right? Different interaction strengths also between particles, amongst themselves, against each other, and so on and so forth. Mostly amongst themselves, okay? So our coarse-grained approach, brute force MD simulation approach, is not really viable for these kind of discovery efforts, okay? So this is where we came up with a much more simpler approach, where we basically coarse-grained your particle, okay, as just spherical beads, basically, that interact with each other through simple colloidal potentials, okay? That's pretty reasonable, okay? and interact with the fluid using the analytical potential. So everything is analytical now, okay? And instead of doing a brute force MD simulation, which is trying to sample, remember we are trying to sample all representative configuration, we don't want to sample. We want the minimum energy or minimum free energy configuration, okay? So we're going to use an optimization algorithm here, okay? Something called a basin hopping algorithm, okay? Which consists of global Monte Carlo moves and local conjugate gradient minimization approach. Okay, of course, this is an approach already used in a lot of these fields and made popular by DJ Wales, but we had to actually develop our own moves that kind of applies to this our particular system, which has kind of some intricacies of this interface. Okay, but ultimately we want to predict directly the global energy configurations. Okay, so in our model, in our simplified model, basically we have simple analytical potentials, and we assume that the strength of these interactions between particles is proportional to R, the radius, which is consistent with basically colloidal theories. Interfacial interactions, I told you, we already model using the theory or the model that we derived earlier. But the key point here is to explore. We came up with 3 key dimensionless parameters that dictate the entire physics of this. Okay, one is obviously the size ratio of the 2 particles. Okay, the other is the interaction strength between particles versus the interfacial tension. Remember that's the competition that you want to model, right? And the third is basically the difference in how this particle likes one fluid over the other, that surface energy difference, normalized by the surface tension between the 2 fluids already. Okay, that's already there. So these are your 3-dimensional, and with these 3-dimensionless parameter, you can now start to explore the entire structure phase. Okay, so here I'm showing you one phase diagram that you can get very quickly. So instead of running months and months of those times, or at least a week for each of these, now you can do everything very quickly. Okay, so all this can be generated within a week or something, or even less than that. Okay, and you can see your characteristic usual suspects, right? So basically what I'm doing here is, before that maybe I should back up, this is basically a cross-section of that structure phase diagram for the condition where the particles are of the same size. Okay, and here I'm plotting basically these structures that you get as a function of that interparticle interaction strength and that miscibility difference. So as you go further up here, that means your particles are getting pushed further and further away from the interface, the 2 layers of particles. Okay, so obviously you're going to start to see monolayers over here, right? Because the particles are very close to the interface, because this is very close to 0. Okay, and interparticle strength are still weak. That the structures, he doesn't want to clump up the structures to gain more interparticle interactions, but lose interfacial interaction because your interparticle interaction is still very weak. Okay, as you go further up along this, as you make the particles more and more different, right? They start to go further away from each other, and you get these bilayer structures. And of course, when you have very strong interparticle interactions, you start to form basically these kind of crystal phases that have already been predicted in aerosols and things like that by DJ Wales himself. Okay, you can see your usual suspects here: hexagonal monolayer, that ridged monolayer that I talked about over here, the hexagonal bilayer. Okay, and under certain conditions, it does form. Okay, the square bilayer and some other interesting structures. Okay, and these have already been predicted. Okay, but that's actually not as interesting. The interesting stuff happens when your size ratio is not 1. Okay, now you start to get very new, interesting emergent phases. Okay, so these are all the catalog, basically the catalog, all the superlattices we got for monolayer superlattices when your chi parameter is still small. The 2 layers, the 2 particles are very close to the interface. One on the other side, the other one. Okay, so you start to form very interesting structures, and some of these actually have been experimented, in fact, reproduced already well before us. Okay, and something I won't talk about here is now my student is also seeing under certain conditions you can form quasi-crystals in these. Okay, but that's a different story. If you push the 2 particles further, meaning your chi parameter is very large, now you form bilayers. This is your boring bilayer, hexagonal. This is your square bilayer, but then you also form other very interesting bilayer structures here. Several of these have not actually been seen experimentally. Okay, although this guy over here, you can actually see that in Islamic art tessellations. Okay, or in Spain over here. There's a lot of patterns like that. Okay, so now we can play the same games that we did with spherical particles with shaped particles now. Okay, so if you recall, let me just check what the time is. Okay, cool. Bit slow, but not bad. Other than just missed the last part of the talk, which is okay. All right, yeah. So if you recall, this particle went directly to the interface and hugged it exactly symmetrically because it wanted to maximize that area, right? So now you can imagine if you have an anisotropic particle, right, like a nanocube over here, it's going to try to sit symmetrically if it's neutral, right, to maximize that area. But it also has the freedom to rotate now, correct, to maximize that. So you would say, well, edge up configuration should be favored because, look, you can occlude the maximum area, right? Okay, let's see what we get, okay? But this is a bit easier. What if we actually had polymers actually attached to them the same way I had? And now you have a polymer that actually likes one fluid over the other. Now your particle gets displaced further from the interface. And now, if you actually rotate the system, actually the areas may not follow this rule, right? It may be very different, okay? So what happens there? So it's not obvious, right? And on top of that, as you're tilting these particles, the chains are coming out at different angles, okay? These chains actually want to be very close. Either they want to really like the interface or they want to absolutely hate the interface and want to go away. That means that as they come out from different angles, they're going to basically lose different amount of entropy to rearrange themselves to either be at the interface or away from the interface, okay? So again, non-trivial effects. So really you need to turn to simulations, okay, to solve these type of problems, okay? So again, we developed a very simple coarse grain model of this. The only additional thing is now our model also models basically this cube shape of the nanoparticle and the steric associated with that, okay? But before that, we had to come up with an algorithm for classifying the orientation of cubes, okay? So we came up with this, my student came up with this very cute algorithm actually. So it involves calculating the two Euler angles of the cube, okay, at the interface. And then from that, you can calculate basically the projected areas of the three faces, dominant faces. Of course, sometimes you won't have one. You may have one dominant face. It's pure edge. Okay? And then what he'll do is he'll do a match of how closely do these three projected areas and their relative area contributions match to a pure face up, pure edge up, and pure vertex up in this orientational phase diagram. I can talk a lot about this. Why is it of this shape, and how do you fold this and have space which is from 0 to 360 degree and 0 to 9 or 180 degree into this non-degenerate space, but that's a different story. But you can basically you can classify arbitrary orientation into either vertex up, edge up, and face up. Okay. Now you have that. You can now start to understand how these polymers are going to affect the orientation, right, of these guys. Okay. So we start off first with our neutral particles, right? Remember we said edge up is favored because it occludes the most. Actually, that's not what we found. We found vertex up is actually more favored. And then it turns out that Marjolaine Dijkstra has also observed this a year earlier with a very different model. Okay, and the reason, so we were trying to figure out what's happening. Why is that? Okay, it turns out that after a lot of detective work, my student found out that the reason is we are assuming the interface is perfectly flat, doesn't have any thickness. Yeah, sure. In that case, edge up will actually give you the. But if you assume a fuzziness of the interface and you assume that it deforms, okay. If you actually calculate the actual area explicitly from these simulations, you will find that the vertex up actually ends up occluding more area. Okay, so indeed, that's the reason why you get vertex up. So again, so it's a little bit of non-triviality actually even with this system. Okay, and then we said, okay, what happens when you have basically grafted? You graft these things with polymers. I'm not going to go into detail here, but basically with grafting based on what is the strength of those grafts, how does it interact with the two polymer layers? Basically, that's what I'm telling. Graft polymer 1, polymer 2, basically the two fluids, and how much you graft, you can basically get all three phases, orientations, vertex up, edge up, and face up. Okay, and we have also deciphered what the reasons for this are, which I'm not going to go into detail, but there are several reasons for why it happens. So we've been able to explain why exactly that happens. Okay, but now that you can control the orientation, can you control the assembly of these particles? Okay, and indeed, you can to some extent. Okay, it does give rise to some interesting structure that you wouldn't see with spherical particles. Okay, the bare particles themselves is very interesting. It wants to be formed edge up, but if it's edge up, you have vertices only to contact, which is very bad. It's not going to form because vertex-vertex interactions are very weak. Okay, so what is this guy going to do? He's going to turn itself, make it edge up, which is not as favorable, but at least with edge up configuration, it has these faces through which it can interact. Okay, so it's going to form these linear chains. In fact, this is a fantastic way to create linear chains of metallic nanoparticles. Okay, which could actually be a real synthesis protocol. Okay, then we said, okay, what about this polymer grafting? Actually, they don't like to assemble generally. They only like to assemble over here and over here. That's it. These guys don't even want to assemble. Okay, whatever assemblies we get, that's basically pretty much it, and one more here. Okay, that's all. Okay, but whatever you get are kind of interesting. This is kind of boring, I would say. It's kind of expected. It's vertex up cubes where they interact through these edges. But these are very interesting and have never been observed. So you form these porous structures with a lot of pores in them, and they want to do that because you have a lot of polymer and they can push their polymer into those pores, and therefore you don't have those steric interactions. So they like to do that, actually. So again, not tested experimentally. Would be great if somebody could do that. Okay, they can also sometimes form these strings that are vertex up. Over here, you can form actually these hexagonal lattices. These are actually not interesting because these are not due to actually particle-particle interactions. These are due to depletion effect. These are because this polymer actually wants to, this polymer is actually non-wetting effectively for something that is very strongly grafted. It doesn't want to go inside. It hates it, absolutely. So it wants to push all these guys together. So it's something called a depletion effect, okay? And you can also, you can play the same games with two species of particles. Unfortunately, these guys don't want to assemble generally. They tend not to. But this is one structure we found which you call a ribbon structure, something like this. Okay? All right. So before concluding, I thought I'll just tell you a couple of directions, but I'll go a bit fast over here, where we are going with this. One thing is we are collaborating with experimentalists to first of all validate some of our computational predictions, but also come up with new strategies for assembling different kinds of matter. Right? Here we are collaborating with Andrea Tao to organize her silver nanocrystals, which have these beautiful plasmonic properties, into these checkerboard arrays, which has never been observed actually so far. Here we actually use hydrophobic interactions also, on top of hydrophilic sort of steric interactions of the polymer. So two species of polymers actually. Here we try to organize metal organic framework particles. These are octahedral into freestanding films that could be used for various applications like separation and so on and so forth. Something else that we are doing is we are trying to use machine learning to build better models of the effective interparticle interactions that account for these multi-body effects, so that you can simulate these things very fast without simulating the entire polymer. Okay, with that you can actually start to predict these interesting phases that people have observed in the bulk. Of course, we want to now apply it to interfaces, right? So that we can now start to predict these type of phases, right? We have only predicted this with our global optimization, but what about phases like this? Okay, because these are purely due to these multi-body effects, which can only be treated correctly with a multi-body potential, basically. So that's what we try to do in this paper over here. Something else we are also doing is we are using neuroevolutionary algorithms. This is work completely in progress, but we're starting to get some interesting results. It's this neuroevolutionary approach that was developed by Whitelam and Tamblyn, basically where you use a neural network to basically parameterize the annealing protocol of how you anneal these systems as you go from high temperature to low temperature, or as you densify the system with compression or something like that. And then you tune the weights of these, or you optimize the weights of this neural network such that it will give you a temperature or a chemical potential profile that will lead to better and better assemblies without less defects. Okay, so stuff like that. Okay, so with that, I'd like to end by just saying one thing. Hopefully, I've convinced you that this interfacial assembly approach of assembling nanoparticles is powerful, potentially powerful, let's put it that way, and could be a useful tool in the future. Okay. All right. So let me now jump to the second part of my talk, which I'm doing actually very well now with time. Okay. So change gears, but the flavor will again be a bit of assembly. Okay. So DNA nanotechnology. Here is my very simple introduction to DNA nanotechnology. Okay, so in DNA nanotechnology, this field, basically researchers use DNA as basically a material, a building block to make devices, nanoscale devices. Okay, by harnessing basically the specificity, the fact that these base pairing interactions are already nanoscopic, so if you can control nanoscopic interactions with programmability, with specificity, then you can start to play around with these sequences and make something interesting. Okay, so I'm going to skip a lot of history of DNA nanotechnology. Okay, but directly jump to the most popular approach that's currently used called DNA-Origami. Okay, in this case, you usually take a long piece of circular DNA, single-stranded DNA that's usually harvested from a virus, M13. It's about 8,000 bases long. Okay, and then you design a bunch of short single-stranded DNA, what you call oligonucleotides, okay? And their job is basically to bind to two distant portions of this scaffold and bring them together. If you intelligently design the sequences of this, you can fold this kind of floppy object into a very well-defined object like that, okay? So with this approach, researchers have been able to create kind of a remarkable array of nanoscale devices, and this is not even up to date. This is like 2015. There's even more cool stuff that has actually done since then. Okay, and I would almost claim there's no other technology that can do things at this nanoscale. Okay, with this precision and complexity. Okay, unfortunately, these structures, they're great breadboards for putting other materials, nanoparticles, studying antibody, antigen interaction, whatever. Like there's a lot of applications. Okay, but these are inherently rigid. So if you think about in the nano world or in your biological world, enzymes, molecular motors, like the DNA packaging motors that I talked about, they're all dynamic, right? In the macroscopic world, machines, engines, dynamic. So they rely on some form of dynamics, okay? So that's one of our interests, okay? How do you introduce dynamics into these stuff? And people have been doing it, not just us, okay? People have been doing very interesting things into kind of introducing flexible entities at strategic positions within these overall rigid structures so that they can either undergo equilibrium fluctuations or fluctuations about some equilibrium points, such as these hinges that our collaborators have developed that fluctuate about certain hinge angle and it's completely tunable. They can make the hinge this way and fluctuate there or fluctuate there, okay? Or things that can undergo, devices that can undergo actually a conformational switch from one configuration to another, which could be useful for drug delivery, such as these boxes that have been created that can open and close based on what they see, a couple of keys that they need to get. So they're lock and key type of mechanism. Or things that undergo perpetual motion based on some fuel that you provide, okay? Like these walkers or these rotors and things like that, okay? Now, to be functional, these things also need to be integrated with other materials like nanoparticles or surfaces, if you are interested in optics and those kind of applications, or membranes and proteins for like biological applications, okay? Furthermore, these guys also need to be self-assembled into higher order structures so you can get some high throughput function out of them or some interesting kind of cooperative effect, right, which you won't get from a single device, right? Maybe they do something together, okay? So in our lab, we are actually interested in exactly those kind of things, okay? And our flavor is exactly the same. Multi-scale approach, simulations, some StatMech, some theory, okay? And so on and so forth with some machine learning, maybe potentially like in this project over here. And we look at dynamics of individual devices, okay? But we also want to look at the dynamics of the self-assembly. How can you self-assemble into higher order structures? Where do the defects appear? How can you remove defects? Stuff like that, okay? And can you extract some interesting function? Okay, so while we have done a lot more work on the device dynamics side, today I thought I'm going to talk about some of our work over here, which is more on the higher order assembly, kind of in the same flavor as what I've been talking about in the nanoparticle world that I just talked about. Right? So specifically, I'll talk about one project we had where we were trying to actually introduce or trying to assemble dynamic structures, like what I showed you earlier, into arrays. And because of these simple interactions between these different devices, you get some emergent effect, emergent phenomena, okay? And I'll talk about that. All right, so let's go there. So the first type of assembly that we wanted to create was something that can exhibit some collective self-organizing behavior, okay? From simple interaction. And we were inspired here by something called the Ising lattice, 2D Ising lattice, okay? So this is the simplest theoretical model, okay, that can capture the phenomena of first-order phase transition in thermodynamics, okay, simplest possible one, okay, and it was originally developed to explain ferromagnetism, okay. So what it consists of is basically spins. You can point up or down. You arrange them in a square lattice. This guy can interact only with the nearest neighbor interactions. If both spins are pointing in the same direction, you get a favorable energy minus J. If they are in the opposite direction, you get an unfavorable energy. It turns out that this very simple model can exhibit a first-order transition between a disordered state at high temperature and an ordered state at low temperature, going through basically this critical point where the heat capacity goes to infinity, basically. Okay, and obviously, Onsager got the Nobel Prize for this, and as well as non-equilibrium thermodynamics. Okay, just to give you an idea what these things look like, here is basically some very simple movies that I created here. What happens when you are above basically this temperature? So everything is basically disordered. So these are spins up and down that I've colored in black and white. So they're fluctuating around. It's like a gas, okay? Over here, low temperature, suddenly these things will phase separate into pure spin up or spin down, whatever color scheme I've used over here. And ultimately, these domains will coarsen, okay? And ultimately, you'll get symmetry breaking and one of those guys will dominate. At the critical point, this guy doesn't know what it wants to be. Does it want to be like this ordered phase or does it want to be disordered phase? Okay, so it's kind of confused, basically, okay? So the question was, can we create an Ising lattice using this DNA-Origami, okay? So if you could do, you have basically a stimuli-responsive material, right? You change temperature or you change this J factor, which is attraction strength, maybe through salt concentration, and you can change between the ordered and disordered, okay? And we think we can do it, in fact, okay? And the reason is the DNA-Origami technology has advanced so much that you can actually create rotors, okay, that can spin around. You can design them in this cross shape, and you can introduce interactions, directional interactions, like what those spins are, Okay, you can put DNA on them. Okay, and the other thing is you can self-assemble them also. Okay, not great, but to some extent you can self-assemble them into 2D array, 1D arrays or 2D arrays. Okay, it turns out that if you put sticky ends, DNA sticky ends, where red, two types that I call red and blue, red can interact favorably with red, blue can interact favorably with blue, but they don't interact with each other. Okay, it turns out you can map this exact system into a 2D Ising lattice. And if you simulate it using Monte Carlo simulations, very simple lattice Monte Carlo simulations, you'll get exactly the heat capacity peak exactly at the temperature that Onsager had predicted. Okay, so it's difficult to see the disordered and ordered, but it's there. Okay, if you look closely. Okay. Now, as we were thinking about it, we realized, well, why do we need to restrict ourselves to Ising lattices? I mean, we can do anything with it. We have all the flexibility. You can have any number of bonds. I don't need to have 4 bonds. I can have 3 bonds, 3 different directions in which they interact, or 2. And I can make arbitrary strength of bonds. I could have 4 here, 1 here, right? And so on and so forth. Okay? It turns out that this simple difference makes this fundamentally very different from the Ising lattice. In an Ising lattice, if you have 2 spins, these 2 guys, whether it's here, whether they're here, whether they're there, they will interact with the same energy, right? But in this case, it matters. Look at this guy. You have a minus epsilon energy here with the bond, but the same thing if you transport over there, it doesn't have any energy. So it's fundamentally very different, okay? And because of this fundamental difference, it gives very interesting kind of phase behavioral properties, okay? So for instance, if you make basically these guys triangular shaped, these bonds, it exhibits, number 1, actually I'll tell that later, but basically it exhibits an order-disorder phenomena between an ordered state here, which is basically just loops. These are 4 of these guys forming a loop because that's what minimizes the energy or maximizes favorable energy, and you form these serpentine-like sort of mazes over here. And the interesting thing is the transition happens at very low temperatures. Okay, and the reason is, number 1, you only have 2 bonds versus 4 bonds, so interaction strength is half. Second is the energy difference between the ordered and disordered state is actually much lower now, okay, compared to the Ising lattice. So you get very interesting for that. Okay, if you just make these one of the bonds stronger, you get basically these kind of these radiating loops and again mazes in the disordered state. If you introduce 3 bonds, it starts to exhibit very interesting phenomena where you get 2 phase transitions. This is the disordered phase. So first it transforms from disordered phase to a partly ordered phase where you have these the ladders still forming, but the rungs are disordered. Here, the rungs of the ladder also start to become ordered. So very interesting effects, okay? And then other effects like this sort of bricklayer structure, okay? But the interesting part is we are now trying to actually experimentally test this through our collaborators, who I mentioned later on. But basically, they were able to successfully create a 2-scaffold system that self-assembles into something like this, which has a base platform in gray and 2 rotors, which I color here differently. They can add some dimerization strand and create a 2x2 lattice, basically, one of these. So basically, you are creating this at high temperature. It should go into that state and low temperature here. So now they introduce those DNA strands that will mediate those interactions, and it forms an ordered state. Of course, we haven't yet tested what happens when you change basically either this temperature or the epsilon parameter. Temperature, you can't do much. Actually, epsilon is what we'll have to change, which we'll do with which. So we are currently trying to optimize the strength of these. Currently, the strength is just too much. So you can't make it disordered, okay? But that's ultimately what we want to do. The second thing we want to do is we want to actually create bigger lattices. So our collaborator has come up with this very cool design of how do you convert that same structure into a 2D lattice. And he's starting to get some promising results, but it's tough to assemble these things. So we are they're trying to come up with approaches to self-assemble these. Okay, so let me very quickly now tell you about the second kind of assembly that again takes advantage of these operative interactions. Okay, something that will be able to communicate a mechanical or signal, let's put it more general, signal from one place to another. Because again, you want to create devices that can do same things that robots do, right? You have something that communicates, right, from one place to another, some sort of information. Okay, so here we were inspired by, I'll be done actually in 2-3 minutes. We were inspired by a phenomena called protein allostery, where if something binds at some location in a protein, it produces an effect somewhere else. It either prevents or enhances binding of something else. Hormones work in sort of this way. Okay, so the way this works is basically when something binds, it changes the conformational distribution of the individual amino acid residues, right? And that conformational change propagates along basically certain path, okay, through this, and ultimately changes the conformation of this binding pocket on the other side. Okay, so at a very simplest, naive level, you could think of it as a domino effect. You take one guy, you roll it, and then that effect will transport, okay, itself. Okay, so the question was, can we create something like this? Okay, if you have something like this, you have a real thing where you can sense something at one place, communicate it to another place, and produce some kind of macroscopic effect somewhere else, right? Which could be very useful, okay, for actuation and other things. Okay, so that's what we wanted to do, and our idea of creating of achieving this is basically this. This is kind of a hypothetical communicating device. It consists of a solid-based platform made out of basically assembly of a lot of these devices, DNA-Origami devices. Okay, and then it has these fluctuating arms. Okay, that are long enough that they can sterically collide with each other, so they can actually alter each other's conformational distribution. And you can also potentially add these stickers or these single-stranded overhangs here that can make them bind this way or that way. Okay, so the idea now is, if you can perturb this input arm, let's say you close it, this guy will not be able to close, and basically its conformational distribution chain, the only place it can bind is over here. So that signal, mechanical signal or mechanical information basically passes along, and you can record it over there. That's the idea. Okay, so to test this, they created a small 2-arm prototype of this, which our collaborators called Steridyne. Okay, so this is basically that. These things can fluctuate. We can also attach potentially these single-stranded DNA pieces to lock them and change their conformational distribution. We can, as I'll show you, we can also change the stiffness of this. Okay, so in fact, that is a key component. We want to understand how these things interact. So you should be able to modulate their conformational distribution at will. And we want to find, if the conformational distribution here, I changed it from this to something else, okay, how did that information pass to the other? And how did the conformational distribution of the other arm change? Okay, so for that, we designed 5 types of hinges. Okay, something that prefer to remain open. By the way, this applies to both left arm and right arm. Okay, some things that remain open, large angles, something that kind of fluctuate around smaller angles, but they can also kind of sample a bit. And then other more constrained kind of arms through these latching interaction, where you actually can almost lock it in the closed configuration. So very strong closing. Okay, and then to see how this system behaves, we created a very simple mesoscopic model of this. In which we account for the steric interactions between the 2 arms, and then we input into it the original distribution. In the end, basically, what we do is we introduce harmonic, or not harmonic, but bending angle fluctuations that match the hinge angle, the hinge angle, I guess, the hinge angle distributions that you observed for arms in the absence of the other arm. That's what we have experimentally. We want to see now, if you introduce both arms together, how are they communicate? Okay, so that's what we are interested in. So we did Brownian dynamic simulation. So here is results for when you force the right arm to be open, right? There was one guy which was open. Obviously, if this arm tries to remain there, this guy can do whatever it wants. It's not going to be affected. And in fact, that's what happens. So your distributions match the dashed line over there, which is the dashed line is the one where you don't have the right arm. But the right arm doesn't do anything, so the distribution remains the same. But as you start to constrain the right arm towards the left side, where the left hinge can now get sterically occluded for certain configuration, you start to perturb this distribution, okay? The more you do that, the more you perturb. Now you actually pushed it. All those close angles are no longer even possible, in fact, okay? Now, these are simulation results, these color maps. These are experimental results, and they match beautifully, okay? The idea is increasing steric interaction from the right arm more strongly. That's the conclusion. More strongly alter the distribution. Now we have done a lot more analysis of all types of possibilities of hinge angles on the left-hand side, hinge angles distributions on the right-hand side. I'm not going to bore you with all this, but basically what I'm going to basically say is if something on the left wants to bind extremely strongly, and the right guy is so weak, it's not going to do much. It's not going to affect the left arm distribution much. Okay? On the other hand, if something never wants to even bind and comes close, I mean, you can put whatever here, it's not going to do anything to it. So nothing happens, okay? So the maximum communication happens is when you have actual intermediate strength of these distributions. So that's basically the message, okay? Moderately latched systems communicate the best, okay? So what are we doing with this? We are now trying to basically polymerize these things into arrays. We are trying to build basically kind of information processing units out of these, where you can actually measure some input in terms of various kinds of factors. It could be something binding, something exerting a force on it, and then you translate that information forward, and then you transduce it into some other form, right? Which could also be a force or something else, to really get to the next level of actually building a kind of a robotic device at this nanoscale. Also, you can potentially also build like AND gates, NOR gates, and things like that. Something I did not talk about is I had a very good postdoc who actually developed a very cool StatMech theory for actually communication between these devices. He couldn't apply it to our problem because we don't have experimental data on kinetics, but he applied it to another related system of cargo transport, and he actually matches experimental results quite well. So hopefully I've convinced you that DNA origami has potential for creating very interesting devices that could start to emulate some of the robotic functions that you see in macroscopic systems. So hopefully I've kind of given you a flavor from the polymer nanocomposite side, how very simple building blocks like spheres can self-assemble into very complex assemblies, which could ultimately have some new functions, which I did not demonstrate. On the other hand, with DNA nanotechnology, I showed you how very complex building blocks, which can undergo dynamics and have rotors and things, can be assembled into very simple lattices and produce very cool functions. Okay, so that's kind of the take home. Most important slide. A lot of the polymer nanocomposite work was all done by Yilong Zhu, who's currently at the Lawrence Livermore National Lab, and with a little bit kind of guidance from an old former graduate student. A lot of the DNA nanotechnology work was done by my current graduate student who just graduated, in fact. He's in fact on the job market, and Sebastian, who's currently an assistant professor at Cleveland State. These are my collaborators at Ohio State and at UCSD on the Nanoparticle project, and Carlos and Michael on the DNA nanotechnology project. So I'd like to end there, and funding agencies. Thank you for it.
Now it's time for questions.
I have a question regarding the polymer grafted on the nanoparticles.
Sure.
Will the properties of the polymer, if you give the properties of the same polymer, like the backbone length or head group, will it have any impact on the ordering?
Everything matters, right? So ours is a coarse grain model. We don't account for those type of effects. Those are more at the molecular scale. So I would still say these are very qualitative pictures of things happening, but you can certainly almost make quantitative predictions if you know what the surface tension is. So what I mean is, I don't need to know how your backbone is changing and what you did, but if you give me like the surface energy through some experimental measure, then we can directly plug it into our model. So yes, at this moment, you'd have to actually do a separate calculation to model the effects that you're talking about, calculate the effective surface tension of that. Right. Now, one thing I should say is all our systems, it's the nanoparticles that are actually mediating the attraction. The polymers are actually just steric. So they don't actually have attraction. Now, if you start to introduce fancy groups, like ionic groups and other things, things that even regular polymers have some van der Waals interaction anyway, those are actually not modeled in our systems. So we try to make it as simple as possible with the fewest parameters, basically. That was the whole flavor. But certainly, you can put in more details. And yes, ultimately, they will propagate an effect, whatever you hope. Yeah. You do. Yeah. Yes.
Thank you for.
Yeah, sure.
Pretty cool. I have a couple questions. Well, really, I'm gonna ask one. Have you thought of this interfacial assembly to do some form of inverse design, where you say, okay, I have this target lattice that I want to make. What can I self-assemble into that?
Yes, we are currently working on that. In fact,
really
exactly. Yes, we are doing it more in the context of quasi-crystals because that's the student is. Yeah, so we are in fact exactly doing some inverse design. So one of the DNA nanotechnology project also actually has inverse design. So what we're doing there is we are putting. So we have an experimental collaborator who has come up with a technique of functionalizing DNA origamis with hydrophobic groups, and these hydrophobic groups. Basically, because they hit water, they tend to cause these origamis to self-assemble. So the question of inverse design question there is, where do you place these patches of hydrophobic groups on this very simple origami structure, like a square tile, such that they'll assemble into some target? So we're actually using machine learning, deep learning-based approaches there, a new method called neural edge joint method. Not developed by us, but by somebody in our program. Yeah. Yeah, exactly. That's a great question. Yeah.
When you talked about the drafting density below, intermediate, and high, relative to what? I mean, when you start drafting these oligomers on the surface, as they come closer, they will extend out.
Right.
So what are you defining one?
It's qualitative at the moment, the way I define it. So I define high grafting as those where basically they will allow nanoparticles to assemble, but they won't allow something else to. So I said, two dimers can still probably interact, despite the fact that you have some steric repulsion, but the particle-particle interaction somehow overpowers that. But when you have a third particle that comes in, you get particle-particle interaction, two of them, so it would want to sit here, but the steric repulsion that arises from the overlap of all these brushes actually is bigger than the sum of the two individually in many cases. And so that means while you'll gain these two particle interactions, the steric repulsion is actually more. So it'll end up actually going to the pole. So we define what we call high grafting as extremely high, they're not even going to assemble. So we call what we call relatively higher grafting density is that allows dimer formation but not others. Intermediate we call things that allow basically these multi-body effects to percolate, to form, like you can form chains of these guys. Very low grafting density is where they allow actually 2D interactions. So multi-body effects are no longer that important. The steric repulsion is actually weak in those cases. So there's no hard and fast rule of what you call you just call it high, medium, and low in that way.
So I have one last question.
Yes.
So you show the hinges and the motors, and is the bar nano wire or nano rod in the slide? The bar.
This one?
Yeah.
Uh-huh.
Are they
That's also DNA. Yeah, that's also
also
DNA.
DNA.
Yes. Yeah, this is all DNA. Like over here, I'll show you. That's all DNA actually. Yeah, it's a different system actually. This is not actually. These arms are actually not the same. These arms are actually L-shaped arms actually.
It looks like a rigid,
It's not. It's actually not. Well, it is like a polymer, but it's semi-rigid. Yeah, but you can see it bends, right? So it has some persistence length, but it's not infinity. Yeah, it's not perfectly rigid. So basically, whatever flexibility you get is from basically. Yes, individually they're actually quite rigid at that scale. So whatever flexibility you get is from basically a little bit of this kind of leeway that you have of like a bending angle right here. Yeah. I mean, we want to minimize it. We don't want it to curl around, obviously, but I think a little bit of it doesn't matter. Right? But yes, ultimately we would want a bit more straighter. If you want to organize like circuits of these things, transform information from one place to another.
Right. So, okay. So as we conclude, let's give our gratitude again for sharing this time today. Thank you.
Thank you all for coming.
Yeah.
Very interesting work.
Oh, thank you.
I'm Dr. Junyo in this MAE department.
Oh, hi, nice.
Yeah, so I'm also doing the MD simulation. So I'm wondering in the cross-grain simulation how
Yeah.
to deal with the polymer 1, polymer 2, and also the ligands.
It's,
on the
again,
particle.
these are very generic models. Like these are Finney chains. Effectively.
Yeah,
Have you heard
yeah.
of Finney?
Yeah.
So we just use those.
Okay.
Oh, you mean how do you create an interface? We do it in a way where
how
they
you-
actually have a repulsive interaction.
how you find those coarse-grain potential parameters.
Again, it's very qualitative. Whatever we do
Okay.
here is very generic models.
Okay.
So what we do is we basically, you have, I think we have Leonard-Jones interaction, if I'm not wrong, between the chains
Okay.
of one polymer fluid.
Okay.
We have Leonard-Jones interaction for the other fluid, but very simple, like Finney chains, basically,
Okay.
with the Leonard-Jones attraction strength. You can basically parameterize it using epsilon.
Yeah,
right?
yeah.
And then we have WCA potentials, which are called Weeks, Chandler, Anderson potential between beads of the opposite kind.
Okay.
That's it. And there's no energy scale for this WCA potential. So the only
Okay.
energy scale is this epsilon. So it produces basically
I see.
a very fluid-like, basically two fluids, polymer melts that don't like each other. It can trap particles. It can undergo
see.
all the right things like capillary waves. Not the true capillary waves, but what I meant by capillary waves is not the true. They have actually long wavelengths. What I meant is just fluctuations actually of the interface.
Sure.
I call it capillary waves, but
Yeah.
technically
It's amazing that
wrong. Yeah.
the model actually matches well with the experiment result, considering such a very simple coarse-grain.
I would actually say
apply.
simple models are the ones that will, in fact. If you try to make it extremely precise, you'll make a mistake somewhere or another.
Right.
And that's when you can actually go wrong. We are trying to do something with the minimal possible models, with the minimum possible parameters. That's always our philosophy. The simplest possible model you can make, like a physics-based model.
The beads that you showed, they
Yeah.
don't represent the monomer in a bulb.
Well, they could mean
I see.
monomers, they could mean a group of monomers,
Yeah.
right? But they don't, so I cannot tell you this is polystyrene. We can try to map the system through the surface tension.
Okay.
Yeah. So if you asked us, apply this to polystyrene and PVP system, which will phase separate, then then there'll be a bit of a problem. Then we have to coarse grain it accurately. But I can say, look, just give me the surface tension of polystyrene or PVP or whatever it is, PEG and poly, which will phase separate, right, into two polymers. That's all technically, that's all I need. Technically.
Nice. And
yeah.
do you account for the flexibility of the chain at all?
Yeah. That is very important.
Because
that's the most
from
important.
One polymer to another polymer,
Uh-huh.
the flexibility of it, two polymers may have very similar surface energy, but the flexibility of the chain will be very different.
Oh, that we don't know. So that'll introduce another parameter then, right? So we want to minimize. We want to make it as generic as possible. Yeah. Right? I mean, if you look at physics theory, right? They say, okay, let's think of this as a spherical particle with some attraction epsilon, right? Yeah, like that kind of a thing. That's what our philosophy is. So it's a bit more physicist approach rather than a chemist approach. Yeah, I think more like a physicist, frankly. I like very simple models. I don't know how to deal with like details and.
The other thing is with the nanoparticles, I would imagine there is in the polymer physics community, the size of the nanoparticle relative to the radius of gyration of the polymer. That
all those are very important.
So do you, when you're defining polymers as a fluid sort of beads, basically, is what I'm thinking it as. And correct me if I'm wrong.
That's correct. Yeah. So they're connected beads. Yeah. Bead spring models.
And so it would matter the size of the nanoparticle relative to how long the chain is, whether it can wrap around or not.
So in fact, that last phenomena that I showed you, right? These nanoparticles were aggregating at extremely high density. Mm-hmm. That's purely because the surrounding polymer, because you have such a high density of this polymers, the surrounding polymer doesn't want to mix with it, doesn't want to integrate with it. So it hates it almost. So you develop a effective surface tension actually between it's called the non-wetting phenomena. I guess that's what you're kind of referring to, right? Because you get this wetting and non-wetting behavior. Mine is because of the grafting density over here. You get a non-wetting effect. The polymer doesn't like actually to wet those guys, meaning it actually hates it. So obviously it'll want to basically pack them together so that it has minimum surface area of interaction with the graft. The one that you're referring to is more of if you have very long, when do you get non-wetting? I think when you have very long free chains and
they can wrap around and they can wet the...
No, actually they don't. I think that is what Sanat Kumar and Peter Green and these
published on this.
Oh, there's tons of work. This is actually I can send you some references.
Right. So from what I recall, reading about the sort of the experimental plus theoretical explanations, when the radius of gyration of the polymer chain is long enough compared to the particle size, then you have a very uniform dispersion of the particles without a significant agglomeration because the polymers are able to wrap the particle, so to speak. If the particle size is large, that the polymer is unable to wrap, the radius of gyration is small, that it is unable to wrap, then you have...
that's one way to think about it. The other way to think about it is the other chains don't want to then wet it in these. In the first case, the other chains don't want to wet it actually because in a spherical particle, these chains are coming out, right? They're getting more area over here. So they start to like kind of compact over here. And maybe at certain graft lengths, maybe these guys don't want to penetrate. They prefer actually to be separate. So that's... No, sorry. No. You're actually saying the opposite. Sorry. My bad. You're saying it actually integrates with the polymer and it doesn't want to assemble. So it's wetted. Okay. Correct. So it's wetted in your case. Okay. So then I guess then the argument changes. I can change it on the fly. You have all these chains and as they are emanating out, you get a lot of space in between them. So the surrounding polymer from the melt can easily interpenetrate that and wet it. And that's what is probably happening. So it's able to wet it. It's favorable, those interactions. So that's why...
molecular weights here. We have to consider the oligomer molecular weight.
Yeah.
I was just talking about the surrounding polymer and the
you have to consider both of them. And the radius of the particle also matters, right? Because it tells you how much space these guys would have when you have polymer pressure on them.
Sorry to interrupt. He has a meeting with the chief.
He
has a meeting with
I'll meet. My name is Arun, by the way, and I'll meet you for lunch.
Oh yes, Arun Kota, right?
Yes, Arun Kota.
Oh yeah.
Very
nice
nice
to meet you.
Thank you very much.
Oh sure. I'm happy to send you some references. So the person you want to look at is Sanat Kumar. He's done a lot of work on this.
So I'm familiar with his work.
Oh, his work. Okay, okay. Yes, yes.
So,
Very important.
yeah, my PhD was in Maryland. I did it on polymer nanocomposites.
Oh, whom did you work with?
Hugh Bruck back then and Srini Raghavan.
Srini, okay. I know Srini very well.
Yeah.
He's a fun guy. Very opinionated.
Yeah. And then went to do a short postdoc with Karen Viney at Penn.
Oh, okay.
And then later now I switched on to surface.
So you have more actually.
Used to be.